So today I'll be revising Unit 2 of IGCSE Physics, all the three subtopics. I'll start with pressure because in the last class, or in the last session, I think I spoke about pressure not that extensively because it also involved gases, which I wanted to pick up in the next chapter. So I'll begin with pressure again. So pressure by definition has the formula force per unit area. And we've discussed that pressure is a scalar for the simple reason that pressure does not act in a particular direction, unlike force, but it does act throughout. For example, so if this is a container containing a certain amount of gas, we all know that the gas molecules collide with each other and with the walls of the container, thereby exerting pressure. The amount of pressure they exert is the force exerted by the unit area. How do we also mathematically prove that there is pressure? Simple. Whenever gases collide, either with each other or with the walls of the container, there is always a change in momentum. And this change in momentum happens at equal or unequal intervals of time, regardless. This change in momentum per unit time proves the existence of force, and the force applied by the gases in all directions divided by the surface area of the wall or the container gives me the pressure. So this is how we mathematically also prove the existence of pressure when a gas applies, or when a gas molecule or when gas molecules collide with each other and with the walls of the container. So coming back to the direction, the pressure is applied by the gas molecules in every possible direction. And when a quantity is present or is applied in all directions, it is direction independent, which makes pressure a scalar. Let's move forward. Now, here are other examples of pressure being applied. So a pressure is applied when a person wearing a football boot is touching the ground. The person's weight in this case acts as the force, and the surface area of the boot is the area, and force over area gives me the pressure. So the same also applies when a knife is being used to cut a vegetable. So as explained here, the surface area on the edge of the knife here acts as the area, and the force applied by the hands acts as the force applied in this case for pressure to exist. So there's a difference between here, the pressure applied by a person of a certain weight on the ground through the boots, and the force applied by a person hand through a knife to cut a vegetable. You'll notice that cutting a vegetable requires a lot more pressure than applying your weight on the ground. And in fact, this needs to have a low pressure so as to not cause any problems to the person's ankle or knees or the joints. So here, a greater pressure is achieved by reducing the surface area. And here, a lesser pressure is achieved by increasing the surface area. The same can also be applied here. So under a tiny area of the point of a drawing pin, the pressure is far too high for the wood to withstand. So here, the whole point of a nail is to embed it inside the wooden plank. This is achieved again by reducing the surface area to a very small value and applying a considerably high amount of force to make sure that a large pressure is created at this point, thereby making sure the the metal nail or the pin embeds itself into the wooden plank. So another way of reducing pressure to increase the area here is by increasing the surface area as explained. So here the surface area A is very high, while the weight applied is considerably less. So you can understand that, again, this football studs had a considerably larger area when compared to a knife, but still pretty much high pressure because the area isn't that much. But here the area is so high that pressure does come down to a great extent. The same can also be seen in the foundations that are laid on any constructed building. The area is increased so that the pressure that the walls or the bricks are able to withstand is very high. The one they're able to withstand is very high, while the pressure applied is very low. That's the concept here, because you're reducing pressure. So now here, a loud spreading washer ensures that the nut is not pulled into the wood when tied up. Again, so these are called washers. So washers, again, are present to increase the surface area, which would instead be much smaller if it were just the net. And when you increase the surface area, the nut is able to withstand a lower or be under a lower amount of pressure as the nut is being either pulled to the left or to the right. Moving on, we also have pressures applied in liquids. So for a liquid, pressure again, as discussed, applies in all directions. So a very simple way to derive the formula is start with the standard formula. Pressure P is equal to force per unit area. One simple way to derive it is we look at all the quantities that depend on pressure. For example, pressure increases with depth, density, and also with the acceleration due to gravity, although that's a constant that we use. So pressure P is proportional to height h. It is proportional to density rho. So converting a proportionality into an equality is just multiplying a constant. Here the constant is the acceleration due to gravity, rho g h. So this is one way. Another way to derive it is just look at force per unit area. I know the force applied by the liquid is nothing but its own weight, which is m into g by area. Now, when you take a liquid in a particular container, let's say that the liquid is filled up to this much height. Now, the liquid also has a certain density and a certain mass, and also a certain cross-sectional area, as shown here. So we all know that density is related to mass and volume through the formula. Density equals mass over volume, or mass is density times the volume. But since volume for a prism is just area times the vertical height, I can write mass as also equal to density times area times height. Substituting this for m here, I get G by A times rho times A times H. So cancelling A in the numerator and the denominator, you still end up with the same formula we wrote before. That is rho G H. So this is the formula for pressure applied by a liquid at a certain depth. And remember, pressure does not depend on the shape of the container. That means a container at a standard height and a container like this, provided they have the same height of the liquid, provided they have the same height h of the liquid and in pretty much the same liquid, they will have the same pressure at the bottom, or the pressure will not change depending on the shape of the container. Please make sure to understand this. So here's an example of pressure P equals rho GH being derived using the same context that I provided this value. I'll hover this on the screen for a minute for you to go through. Let me move forward. Next, here we discuss hydraulic systems. So hydraulic systems, as discussed, work on a very simple premise. Let's say you're trying to lift an object that is, let's say, 120 Newton, or or close to 120 Newton in terms of weight. But let's say the force that you're able to apply is just upwards of 12 Newton. So force applied is just 12 Newton, but you wish to lift an object that's pretty much 10 times your applied force or weight. So how do you do this is you use the concept of a hydraulic lift. A hydraulic lift has two entrances or an entrance and an exit. The gap is filled with a liquid of a certain density. And here in this case, it's oil. And here at the entrance, you have an input force acting through a piston. And here's an output force again through another piston, which is being used to lift the heavier object. So it works on the premise that because pressure is scalar and pressure is same throughout this entire liquid here, the pressure applied here, let's call this P1, is exactly going to be the same as pressure applied here, that is P2. Or it works on the premise that pressure P1 is equal to pressure P2. But pressure P1 is equal to the applied force F over, let's say, this smaller area A1 equal to the weight of the body over area A2. So here, if you notice, they've taken a numerical example here. The area is 0.01 meter square and here it is 0.1 meter square. So rewriting the formula, I get W by F equals A2 by A1. So as long as this ratio A2 by A1 is a value greater than 1, I can use this to push the body. I can use a much lesser force to push a body of a much higher weight. For context here, the multiplier is 10. The area multiplier is also 10, making sure the pressure remains the same. So this is a force multiplier. Now, if you're wondering where this extra energy comes from, there is no extra energy. In fact, energy transfer will be the same. The simple reason is, let's say here, work done W1 is equal to F into, let's say, displacement D1 here. Here, let's say W2 is the weight W into displacement D2. As you can notice here, because F is much smaller than W, the displacement D1 is much, much, much higher than compared to D2. In other words, the work done will be balanced or energy is conserved due to the fact that the displacement D1 for a much lesser force is much higher than displacement D2 for a much heavier force. In other words, if you were initially able to apply a force to push the piston down, let's say by 10 meters, the body or the object of weight 120 Newton will just move over a distance of 1 meter. That's it. So F by W will be equal to D2 by D1. That's it. This is how energy is conserved in this interaction. Now, as discussed, pressure applied by air does act in all directions, and atmospheric pressure that acts at sea level is considered a constant value. In fact, if you want a more precise value, the atmospheric pressure for all numerical calculations is taken or is assumed to be a constant value of 1.013 into 10 to the power of 5 Pascal or 100 kilopascal or 1 into 10 power 5 Pascal approximately. So this is the value of atmospheric pressure we take for sake of all numerical calculations. Moving on. So the standard atmospheric pressure, there are different units of measuring this. Like I said, Pascal is the standard or the SI unit. Apart from Pascal, there is millimeters of mercury. There is also ATM. So the value of atmospheric pressure, which I spoke of, which is 10 to the power of 5 Pascal, can also be written as 1 ATM. ATM is a unit of measure of pressure. Or I can also write this as 0.760 meters or 716 millimeter of rise in level of mercury or hydrogen. So these are different ways in which I can measure the atmospheric or depict, the atmospheric pressure. SI unit Pascal. Other units include atmospheric ATM or millimeters of mercury. Next, a manometer. A manometer is a device which is sort of used to measure the pressure. It measures the pressure by accurately denoting the difference in the pressure between the two quantities or the two things whose pressures are depicted in the manometer. So let's understand how this works. So a simple manometer looks like this. As shown, there are two inputs. So usually this input is the atmospheric pressure. And here is the input, let's say P1 pressure that needs to be measured. So simple. So this column is filled with usually mercury or any other liquid. So if you notice that the level of mercury is much lower on this side when compared to this side, that means pressure P1 here is going to be greater than the atmospheric pressure. That is how pressure P1 is able to drive this level of liquid to be a much lower value than this. So how do I measure the pressure exactly? Simple. One of the quantities that is on the right here is a known value. We know the atmospheric pressure. So all I need to do is find out the difference in the height. So the difference in the height is nothing but the difference in pressure levels between P1 and this known value of ATM. So all I need to do is P1 minus the known value of atmospheric pressure will be equal to the pressure, the difference in this pressure, rho GH. Sorry. So rho times G times H. This H value is the difference in the height of the levels of the liquid on either side of the U tube or the column. So using this, I can measure P1 because ATM is a known value, rho density of the liquid is a known value, G is a constant, and H is a value that is measured and evidently known. This is how a manometer works. Looking at gas laws, let's start with gas laws here. So Boyle's law tells us that for a gas, pressure and volume have an inverse relationship. Pressure and volume have an inverse relationship, which means pressure is inversely proportional to volume. And if I plot a graph of pressure versus volume, it's going to be a curve of a similar shape as shown here. If I plot a graph of pressure versus 1 by volume, however, this graph will be a straight line passing through the origin. This just tells me that, okay, you can notice here that the slope m is constant. Slope m is a constant value. And how do you find slope? Slope m is nothing but it is the change in y quantity versus the change in x quantity. Or you can write this or rewrite this part as pressure P times volume V is a constant. This is exactly how this works. I can also rewrite this as, let's say, pressure P1 at volume V1. Let's say at this point, the pressure here was P1 and the corresponding volume was V1. This will be equal to pressure P2 at another random volume V2. P1 V1 equals P2 V2. You can use this in a numerical where you are asked to calculate or given one set of values of pressure and volume and asked to find another value of missing pressure given the volume or another value of missing volume given the pressure. So this is Boyle's law. Here, I'll hover over this for a minute so you can take a look at Boyle's law. Again, here's an example using the same concept. I'll hover over this too for a minute so that you can take a closer look at the example being solved. Let's move on. We already covered work, power, and energy, and also efficiency in the last class. Please give it a revisit if you're unsure of the concepts. Now, let's move on to solids, liquids, and gases. So from a molecular level, there is a specific difference between solids, liquids, and gases. The difference is that solids have a fixed shape and also a fixed volume. That is also because solids are, or the molecules in a solid have a lattice structure which keeps the molecules fixed in position and they are not able to move. They can only vibrate in a given position. The lattice structure also provides layers which are bound to one another. Forming the lattice structure that I spoke of, and thus they have a definite shape and a definite volume. So the lattice structure or the layers being bonded to another are through chemical bonds. For example, in water, which isn't a solid but a liquid, however, the weak van der Waals force acts as the bonding for the layers. Sorry. Now, moving on to liquid. Liquids have definitely a fixed volume, but not a fixed shape. The simple reason being, I just give the example of water, in which a weak van der Waals force acts as the bonding layer or bonding layer for, or acts as the bond, sorry, for different layers. But the weak van der Waals force is so weak that the layers tend to slide over one another, thereby making a liquid have a fixed volume, but not a fixed shape. In fact, here we speak of the vibration of the liquids being much stronger than that of solids. In fact, it's much stronger, so that the attractions cannot hold them together in fixed positions anymore. Thereby, the molecules move past each other or the layers slide over one another, again, giving rise to liquids not having a definite shape, but still a definite volume. In a gas, however, the molecules are so far apart and the intermolecular forces are so weak that they neither have a fixed shape nor do they have a definite volume. And they instead fill the space that is available within the container in the form of shape and in the form of volume as well. The molecules, as spoken before, are spaced out and the intermolecular forces are pretty much non-existent, unlike the case in liquids and solids, where intermolecular forces are increasingly stronger in that order. So here's the presence, or here's the arrangement of molecules for solids, liquids, and gases. Since it is not given in syllabus, I'll not be looking at other states of matter, such as Bose, Einstein condensate, liquid crystal, plasma, all of these. Next, let's understand what is Brownian motion. Brownian motion, as shown or as depicted here, is the random motion of the molecules, specifically in fluids, that is liquids and in gases. Brownian motion is the random or the zigzag movement of molecules, which is again brought forth by weaker intermolecular forces. absence of strong bonds or lattice structures thereof. And again, this is the reason why solids or molecules in a solid do not show or depict Brownian motion. This specifically happens in fluids, that is in liquids. This is seen specifically in liquids and in gases. Moving on. Now, here we speak of the energy of the molecules. Here we speak of the difference between the internal energy and thermal energy. So the sum total of the kinetic and the potential energy of all the atoms in a material is called its internal energy. Mathematically speaking, internal energy is the sum total of potential energy plus kinetic energy of all the gas molecules. Now, if a hot material is in contact with a cold one, the hot one cools down and loses internal energy, while the cold one heats up and gains internal energy. This happens through the process of conduction, which we will discuss going further. And this energy transferred is in the form of heat or thermal energy. So thermal energy is often used both internal energy and heat. In other words, thermal energy can exist or can be described as internal energy and as heat, depending on the context that is taken. Forward, here we discuss what is temperature. In simple words, most textbooks define temperature as the degree of hotness or coolness of a body. Temperature has the Celsius scale and, for context, the Kelvin scale as well, which is its SI unit. I'll not be discussing Fahrenheit because it is not one of the common units that we use. So in a Celsius scale, we usually take Celsius scale from 0 to 100, where 0 is usually the melting point of ice, or always the melting point of ice, and 100 is the boiling point of water. The Celsius scale is usually denoted from 0 to 100, or a little bit more, like from -10 to 110 degrees. And there is a liquid that is used with a certain constriction here. And the level of rise of the liquid when exposed to a certain environment of a certain temperature depicts the temperature of that particular environment. This is simply because the temperature of that surrounding is transferred to the liquid through the process of conduction. And as the liquid gains temperature, it starts to expand, thereby showing a depicted value here. The liquid is able to stay at a depicted value for a certain point in time due to the constriction here, which holds the liquid in position until the measurements or the recordings are taken. Along with Celsius scale, we also have a Kelvin scale. So the conversion from degrees Celsius to degree Kelvin is very simple. All you need to do is, if you have a value X in degrees Celsius, you just need to add 273 or 273.15 to be precise to get the corresponding value in Kelvin. The absolute zero temperature is defined as 0 degree Kelvin, or consequently -273 degree Celsius. Again, if you want to convert degree Kelvin into Celsius, just -273.1. That's it. Here you have a thermocouple thermometer, which can be used to measure temperature. A simple explanation of how this works is, here it is made up of two wires as seen here. So now here you have a cold junction, and here the probe contains temperature sensing junction, or this is the part that is immersed in a liquid or exposed to an environment whose temperature is supposed to be measured. Just remember that copper wire, along with any other conductor, has different levels of electrical conductivity when exposed to different temperatures. And because these two wires are exposed to different temperatures, there is a difference in the amount of charges or the amount of current that is passed through both these wires when they're exposed to these varying temperatures. And the difference in the amount of charge or the amount of current that flows can be used as a straightforward indication of the surrounding temperature. This is a simple explanation of how a thermocouple thermometer works. Here again, as explained, the temperature difference between the two junctions causes a tiny voltage. Again, how does voltage persist? Because a difference in flow of current. Again, because current flows, there is a voltage, let's call this V1 and let's call this V2. There is a difference, a change in current causes a change in voltage or a potential difference to be developed between the two junctions. And this potential difference, again, can be used as a direct measurement of the temperature. This also works because voltage by definition is work done per unit charge or energy consumed per unit charge. So voltage or potential difference is a direct indicator of energy or temperature. We've discussed what temperature is. In simple words, it is the degree of hotness or coolness of a body. In a more abstract sense, it is the average kinetic energy per particle of a gas or a liquid or a solid. And consequently, the higher the test set temperature, the greater the average kinetic energy per molecule. Next, this is what I discussed in Kelvin scale. Converting Celsius to Kelvin is just adding 273. Converting Kelvin back to Celsius is just subtracting 273. Absolute zero is just 0 Kelvin or minus 273 degrees Celsius. Absolute zero is defined as the lowest value of temperature that is achievable, which is minus 273 degree Celsius or 0 Kelvin. Again, because 0 degree Celsius is the transition from ice to water or water to ice, it's called a lower fixed point in a temperature or a thermometer, sorry, also known as the ice point. The 100 degrees Celsius, which is the boiling point, is the upper fixed point, also known as the steam point. Now, let's talk about liquid in gas thermometers and certain quantities which are associated with them. I'll explain in very simple words. You can pause and read through all the definitions given. Sensitivity is the ability to respond to the smallest amount of change in temperature, in this case, in the surrounding environment. That's all sensitivity is. It is the ability to respond. Not when I say respond, I mean record. For a thermometer, it is ability to respond or to record the smallest change in temperature T in a surrounding. So the greater the sensitivity, the greater the ability of the thermometer to record the smallest change. Range. Range is, technically speaking, it's the highest value minus the lowest value in a thermometer. The greater the range or the higher the range of a thermometer, the more values it can take into account or it can show the thermometer. For example, for liquid in glass thermometers, even though sometimes, yes, we use alcohol, we use mercury mostly because mercury freezes at minus 39 degrees Celsius, whereas alcohol freezes at a much lower temperature of minus 115 degrees Celsius. But since we never go to minus 115 degrees Celsius normally under normal circumstances, we usually have liquid and in glass thermometers made up of mercury. Although sometimes, like I said, we also do use alcohol. And mercury thermometers also have an upper limit of 500 degrees Celsius, which is higher than that of alcohol thermometer. Responsiveness is the ability to respond more quickly to a change than others. Remember, sensitivity is the ability to respond to the smallest change, but not the speed at which you respond. The speed at which you respond is the responsiveness. The faster your liquid in glass thermometer is able to rise up and go down when subjected to different or changing environments or changing temperatures, the greater its responsiveness. Linearity is the ability of the thermometer or any device in general to respond linearly to a change in temperature. For example, liquid in glass thermometers work by increasing the mercury level as temperature increases. So if the rise in mercury level, is directly proportional to the change in temperature, then the liquid in glass thermometer is supposed to have a high linearity. That means if the mercury level, let's say, rises by 10 millimeters for a change in temperature from 20 degrees to 30 degrees Celsius, if the change stays at 10 millimeter or thereof for a subsequent change from, let's say, 40 to even 50 degrees Celsius, it is the same change, then the linearity is said to be very high, or the in glass liquid thermometer is said to be linear in terms of its temperature depiction. Now, next we look at expanding solids and liquids. So remember that solids and liquids do not expand at the same rate, owing to the fact that their molecular structures are vastly different. So now remember that here you can see an example here. Steel rods can be used to reinforce concrete because both materials expand equally. If the expansions are different, steel might crack the concrete on a hot day. In an ordinary glass dish, if an ordinary glass dish is put straight into an hot oven, the outside of the glass expands before the inside and strain and cracks the glass. Pyres expand much less and should not crack. In other words, we usually bind solid materials which have a same rate of thermal expansion. Obviously, thermal expansion of liquids is far greater than of solids, owing to the fact that solids have a stronger, much more evident, and more, I would say, stronger lattice structure. In fact, liquids do not have a lattice structure, which is why they don't have a definite shape, owing to which liquids can expand far easily or far quicker for a lesser amount of heat or energy supplied than compared to solids. Obviously, solids have a much less thermal expansion capacity when compared to liquids. Another reason will also be the fact that the intermolecular forces are much weaker in a liquid and a gas when compared to a solid. Again, here's another example of thermal expansion being taken into account for a practical use. So here the overhead cables are suspended from poles or pylons. They're left slack. You might have noticed this. The left slack slow partially or partly to allow for the contraction that would happen on a very cold day, and subsequently the expansion, which causes more slacking on a hot day. Another application of the thermal expansion is a bimetallic strip. So bimetallic strip is usually a strip that is used to break contact in a circuit when a current value increases over a prescribed value. So remember, in a circuit, when a larger amount of current starts to flow, this corresponds to a greater temperature rise in the bimetallic strip and in all parts of the circuit. And whenever current crosses a certain threshold or a prescribed value, the temperature increase will be so much such that the bimetallic strip, which is made up of two different alloys, will start bending owing to the fact that the two different alloys have different thermal expansion capacity. Here, it seems like brass seems to have a a higher thermal expansion capacity when compared to Invar, which means brass, you can see, has expanded much more than Invar, owing to the bimetallic strip bending as shown, thereby breaking the contact in an electric circuit. So when the current exceeds a given threshold or a prescribed value, the contact is broken as such, going to the bimetallic strip, and thereby protecting the circuit from the dangerous current, which would have instead flown in the circuit and maybe caused temporary or permanent damage to the electrical appliance which is in use. Now, here we have, after Boyle's law, the next one is a Charles law that gives a relationship between pressure and temperature. As evident from the graph, you notice that pressure and temperature have a direct proportional relationship, which can be written as pressure over temperature is the slope, which is constant, or pressure P1 over temperature T1 is equal to pressure P2 over temperature T2. The reason this is not a proportional relationship of the form y equal to mx, but instead y equal to mx plus e is because pressure becomes zero at absolute zero temperature. Is at minus 273 degrees Celsius. In other words, the y-intercept is at, the x-intercept, is at minus 273 degrees Celsius or 0 Kelvin. If you were to represent temperature in Kelvin, then the y-intercept would be at the origin. Again, this is Charles' law. The last law is in fact the Gay-Lussac's law, which I'll speak about for a minute and then give you the brief. So Gay-Lussac's law tells us that volume V, although not explode much, you need to remember that volume V is also proportional to temperature, specifically for a gas. Again, can be written as V by T equals constant, or V1 by T1 equals V2 by T2. So to sum up, pressure and volume inversely related, pressure and temperature directly related, volume and temperature directly related. If all three are varying, then pressure into volume over temperature will be equal to a constant. This is called the ideal gas equation, which you will learn about in higher classes if should you choose continue with physics. It can also be rewritten as P1 V1 by T1 is equal to P2 V2 over T2. This formula applies if and only if all the three quantities are varying. Whereas you have pressure P into V equals constant. That is if temperature T is a constant. Again, you have pressure P over temperature as a constant. That is if volume is a constant, and volume V over temperature T as a constant if pressure is a constant. If none of them are constants, then P1 V1 by T1 equals P2 V2 by T2. Although yes, I am staying away out of syllabus, so you do not have to remember this particular concept. So I'll give you a small break, post which we'll look at the three methods of thermal conduction, which is uh, thermal energy transfer, which is conduction, convection, and radiation. Let's continue with the concepts. So let's look at thermal conduction. Like I said, there are different forms of energy transfer. I'll start with conduction first. Thermal conduction is the energy or is a form of energy transfer when there is a direct contact between the two bodies. Right? Obviously, if there is a difference in energy levels, that is, if there is a hot body that is in touch with a cold body, the energy will transfer or will be transferred from the hot body to the cold body. This can happen within a single body as well, where the hot end, which is much hotter, transfers energy to the cold end. This is pretty much how thermal conduction occurs. Next. Just remember, thermal conduction is through direct physical contact. Now, based on the ability of the bodies to conduct heat, they are classified as conductors and insulators. Materials which readily conduct heat are called good conductors or just conductors. The materials which do not readily conduct heat are called insulators. Most metals, in fact, all metals are examples of conductors, whereas plastic is one common example of an insulator. Wool is also an example of an insulator. So as explained, metals are good thermal conductors. Non-metals are mostly poor conductors, and liquids also fall into that category. Gases, in fact, are far worse conductors or very good insulators. The simple reason why liquids and gases are not as good conductors as solids in general is owing to the fact that in liquids and gases, the molecules are farther apart, and thereby the energy transfer isn't as effective as it would be in a solid, because the molecules are confined in a lattice and only allowed to vibrate, thereby allowing for energy transfer to occur far, far more effectively or efficiently. Now, the simple way how materials conduct is mostly through the sea of free electrons. Especially in a solid, when the ability of the molecules to move is pretty much non-existent and they're only allowed to vibrate in a fixed position. The free electrons are what carry the energy from one end of the solid to the other. They mostly just drift between the atoms, as explained here. And because they're given energy, they get kinetic energy, and they're sped up as they move throughout. And as they move to the farther end where energy is far scarce, they do settle down, transferring the energy to the molecules so that through collision, so that the molecules or the atoms can continue to vibrate. This is how energy is transferred, in fact, most effectively through metals from one end to the other. So an electric current is a flow of electrons. So metals are not only good thermal conductors, they are also good electrical conductors as well. Because again, as discussed, it is the electrons that carry over the electrical energy from one end of the metal to the other. Convection. So convection is another unique form of energy transfer. So here you can take an example of a beaker containing a certain liquid being heated gently in one place. So now as the water above the flame becomes warmer, it expands and becomes less dense. So here you take an example of water in a beaker, which is subjected to heat through a flame. So they say the water that is closer will get heated up, and this layer of water. So this layer gets heated up, and as it gets heated up, it becomes less dense. And as it becomes less dense, it starts to rise up. And the much denser water comes down and then gets heated up. This cycle repeats, causing what we call as a convection current. So as water is heated, the molecules of water, which break free from the weak van der Waals force, gain energy and vibrate more rapidly. And as particles circulate, as explained here, the energy is transferred to other parts of the beaker as well. So convection does not occur if the water is heated up at the top rather than the bottom. Simple reason being, the less dense molecules always stay at the top, which means if you continue to heat the top, it's the same layer of molecules or water that will continue to get heated up, thereby not allowing the circulation as it would when heated from the bottom. Convection in air also occurs. Convection in air occurs specifically as a gas as well. Warm air rises when and as is displaced by a cooler, denser air sinking around it. We will notice an example going forward where convection in air is the cause for the land breeze and the sea breeze. So remember, as warm air gets displaced by colder, denser air, there is a huge convection current in the Earth's atmosphere. This is what causes the winds across all the oceans and the continents. Convection also causes onshore, offshore breezes. Again, like I said, land breeze and sea breeze, which sometimes blows during the summer. Let's discuss how land breeze and sea breeze occur. So during the day, I'll explain the setup as is. During the day, the sun's rays, remember, will heat up the land far quicker than the sea. So warm air will rise above the land and it is displaced by cooler air moving in from the sea. So the air near the land is much warmer, and warmer air will rise up and go towards the sea. The cooler air from the sea will take the place of the warmer air. This is the cooler air. And again, as warm air flows towards the sea, it becomes cool. Again, cooler air will sink and then again go towards this. This is what causes a this is what causes a sea breeze. Next. The opposite of this is a land breeze. This exactly happens as shown. At night, the reverse happens. The sea stays warmer than the land, or in other words, the land cools much faster than the sea. Due to this, warm air will now rise above the sea. It will blow towards the land, called as a sea breeze. And again, this will sink, causing a land breeze to go away from land to the coast. This is simply owing to the fact that the sea is much warmer than the land at night, whereas the land is much warmer than sea during the daytime. These are what cause the land breeze and the sea breeze. Next, the last form of energy transfer is through thermal radiation. Remember, for thermal conduction and convection, there is an important necessity for an intervening medium which helps transfer of energy. Thermal radiation, however, is that form of energy transfer where the energy occurs through electromagnetic radiation. And we will understand when we go to waves that electromagnetic radiation, electromagnetic waves do not require an intervening medium for propagation, meaning which thermal radiation is a form of energy transfer where there is no requirement of an intervening medium. The simplest example is how the energy from the sun is transferred to the earth through thermal radiation, through empty space or vacuum, without there being the presence of any intervening medium. And most of the thermal energy is carried through infrared waves in the electromagnetic spectrum. Remember, black bodies are best emitters, best absorbers, but worst reflectors. Whereas shiny silver surfaces are worst emitters, worst absorbers, but the best reflectors. Please remember this. This is one of the reasons why you are asked to wear black woolen clothes during the winter and white or light shiny or silver material during the summer. Now, here's the construction of a vacuum flask. A vacuum flask consists of three noted equipments: a stopper, a gap, which is usually with air removed, glass or steel walls, and silvery surfaces. So all of these have a specific purpose. Let's explore what each one is. So now, an insulated stopper will reduce the amount of conduction and convection, or it will reduce the amount of energy that is transferred to the surrounding environment. A double-walled container with a gap in between, specifically a gap made of vacuum, will reduce transfer of energy or dissipation of energy to the surrounding environment. And the walls are made up of silvery surfaces so that the amount of thermal radiation is reduced. As we've discussed in the previous screen, the silvery surfaces are bad emitters, which is advantageous because energy needs to be kept within the flask. Bad absorbers, yes, which is again an advantage because energy should not be dissipated to the surroundings. They are good reflectors so that the energy that tries to go out is reflected back and kept within the liquid, which is usually kept at a hot or a cold temperature, thereby making sure the temperature does not reduce or increase much. If it's a hot body, the flask makes sure the temperature reduction isn't as much. If it's a cold body, it will make sure the temperature increase isn't much. That's what a flask is. And every single construction is pointed towards that. Next, let's talk about evaporation. Evaporation is basically the conversion of a liquid state of or a material in a liquid state to a conversion to a gaseous state as below its boiling point. So remember, evaporation occurs at all temperatures. Evaporation does not occur at the boiling point. Evaporation occurs at all temperatures. Next, here are some ways in which liquids evaporate more quickly. When you increase the temperature, wet clothes dry faster on a warm day than they do on a closed day. Increase the surface area. That's why when you a wet puddle, a larger wet puddle will dry out more quickly than let's say water in a glass, for example, kept in the same surrounding environment. When you reduce the humidity, also yes, evaporation occurs faster. If you notice, this is one of the reasons why if you go on vacation to, let's say, a place like Goa or any place with a beach, you'll notice that even though it's so hot outside, your clothes left out to dry will not have dried as fast. That's because of the high amount of humidity in the atmosphere. Blow air across the surface, yes, that clothes do dry faster when air is blowing. Again, if the humidity is high, uh, blowing air does not help much. Boiling. Boiling is a very rapid form of evaporation. When water boils, the vapor bubbles form in the deep inside the liquid. They expand, rise, burst. Remember, at 100 degrees Celsius for water, the vapor pressure in the bubbles is strong enough to overcome atmospheric pressure. Bubbles start to expand and boiling occurs. Remember, boiling occurs at a particular point. Evaporation occurs throughout at all temperatures. Evaporation occurs only on the temperature on the surface. Boiling occurs throughout the liquid. Please remember these changes. Next, you have the cooling effect of evaporation. Evaporation also has a cooling effect. For example, when you wet your hands, the water on your hands starts to evaporate. And as it evaporates, it takes thermal energy from the surface of your hand, leaving your hand to be cool. You might notice this you might notice a drastic effect if you put petrol on your hands. You notice that if you uh, do in fact have a small minute amount of petroleum fall on your hands, you'll notice that it gets cool very quickly. That's because petrol takes energy, draws energy from the surface of your skin at a much faster rate than water does. This is why if you pour water or petroleum over your hands do feel. Condensation is the opposite of evaporation. It's the conversion of a gaseous state into a liquid state. Remember, you will have noticed this when water vapors start to form on the walls of a container as temperature decreases. And as temperature decreases further, all of the water vapor in the atmosphere gets converted into water. And again, if you reduce temperature even more, condensation leads to liquid state becoming a solid state through the process of freezing. Let's talk about specific heat capacity and specific latent heat, and thus conclude our topics for today. Now, if I were to draw a graph, let's see, of energy versus temperature for a certain body, this is what I would expect to see. Let me show you what we expect to see. Let's say you plot a graph of temperature versus energy supplied. Let's say you start with water. We all know the water has its melting point at 0 degrees Celsius. And let's say its boiling point at 100 degree Celsius. Let's say I take water at minus 10 degrees Celsius. Now, as I supply energy to water at minus 10 degree Celsius, water will constantly increase in temperature as it rises to about 0 degree Celsius. Let me show this with a different color. It will constantly rise in temperature as it absorbs energy and goes to 0 degrees Celsius. Uh, one mistake I made, please make sure it's ice at minus 10 degrees Celsius, not water. So as ice increases in temperature, as ice absorbs energy, it also increases in temperature from minus 10 degrees to about 0 degrees Celsius. At 0 degrees Celsius, it will undergo a change in state. And as it undergoes a change in state, please notice that the energy supplied will no longer cause a rise in temperature, but will instead cause a change of state, thereby making sure the temperature remains the same. Beyond this, again, when all of the ice here has converted into water here without raising the temperature, now it is free to raise its temperature from 0 degrees Celsius to about 100 degrees Celsius. And the specific heat capacity is actually higher, which means it takes a lot more energy, which means I'll draw a smaller graph. The raise in temperature is much slower. Let me explain the concept first before I do. So specific heat capacity is denoted by the formula C. It depends on energy supplied. It is inversely dependent on mass and the change in temperature. So written as Q is equal to MC delta T. So I can rewrite this formula as change in temperature equals change in temperature equals 1 by MC into Q. Here, remember, this is a graph of change in temperature versus energy supplied, which is Q, delta T versus Q. So here 1 by MC will be the slope. We both have the specific heat capacity for ice is about 2100 joule per kg per degree Celsius, whereas specific heat capacity for water is a slightly, in fact, it's a double higher value of 4200 joule per kg per degree Celsius, which means the energy or the increase in temperature from water to water vapor, that is from 0 to 100, will be much slower, going to the fact that C is much higher and the slope is 1 by MC. So higher value of C means lower value of slope. So here is your mathematical proof of what I'm about to draw and why I'm about to draw. So the temperature change will be much slower. Please notice. And this stops at 100. And here, please remember, initially it is in the form of water, but eventually it becomes water vapor. So it stays as water here, but it transforms into water vapor, which is the gaseous state. Or in other words, ice to water, melting, water to water vapor, evaporation. Water vapor to water would be condensation. Water to ice would be freezing. Again, beyond this, a further application of heat will cause an increase in temperature as shown. So what do we understand from this graph? We understand that whenever there is a change in temperature, there is no change in state. Whenever there is a change in state, there is no change in temperature. So this, again, concludes in the same formula that I wrote beforehand. That is, Q is equal to MC delta T or delta theta, depending on which textbook or denotation you're following. Doesn't matter. So here Q is the amount of energy supplied, M is a mass, C is the specific heat capacity measured in joule per kg per degree Celsius or degree Kelvin. Delta T is the change in temperature. Students, please make note. I know Kelvin and Celsius are different units and the conversion is different, but change in temperature will be the same whether in Celsius or Kelvin. Or in other words, the change in temperature is 15 degrees Celsius. It is also the same in Kelvin. This is because you subtract the two temperatures. So even when you add 273 and subtract the two quantities, they're going to remain as the same quantity. So when it comes to change in temperature, Celsius and Kelvin won't matter. The value will be the same. Don't try to add or subtract 273. For change in temperature, for just temperature, yes. From Celsius to Kelvin, add 273. From Kelvin to Celsius, please make sure to subtract 273. So specific heat capacity is all these. The ones highlighted in red are specific heat capacity. The ones highlighted in green, where there is no change in temperature because there is a change in state, is specific latent heat. Please notice the formula is Q is equal to mc delta T. So here, for example, you have the concept of just thermal capacity or heat capacity. There is a difference between specific heat capacity and just heat capacity. Students need to really nail the difference. Let's look at it first. Specific heat capacity. Specific heat capacity is the energy required to change unit mass of a substance or temperature of unit mass of a substance through unit or 1 degree Celsius. It is denoted by the symbol C, which is equal to Q divided by M delta T. Just heat capacity or just thermal capacity is different. Just heat capacity or just thermal capacity is different. It is denoted by M into C. It is denoted by M into C together, which is just Q by delta T. It has the energy required to change the temperature of any substance to 1 degree Celsius. The word unit mass goes away because M is being multiplied here. Specific heat capacity is C equal to Q by M delta T. And thermal capacity is MC, which is just Q by delta T. That's all it is. Again, power is denoted by heat as power equals energy by time, or Q divided by time T. Energy Q is also power into time. Please make note of these changes. Please understand the difference between specific heat capacity and just thermal or heat capacity. This is the difference. The last concept is latent heat. Remember, latent heat is, again, if you go back to the previous diagrams I drawn, latent heat is the energy that is transferred during a change of state. There are different latent heats values. Latent heat, the energy that is required for a transition from solid to liquid is latent heat of melting, which is going to be the same as the reverse transition, which is latent heat of fusion. The energy required or the energy required by unit mass for a change of state from liquid to gas is latent heat of vaporization, which is same as latent heat of condensation, which is the opposite or the inverse. Formula is very simple, although out of syllabus. Latent heat L is equal to Q divided by M, or rewritten as Q is equal to ML. Q is the amount of heat supplied, M is the mass, L is a latent heat or specific latent heat, which is either of melting, fusion, vaporization, or condensation, doesn't matter. Example, the latent heat of vaporization for ice is about 338 kilojoules per kilogram. Here's the graph again that I showed. So remember that whenever temperature change is observed, it is specific heat. Specific heat. Whenever there is no change in temperature observed by unit time, in spite of energy being supplied, this is latent heat. Please make sure you understand the differences between them. So this is latent heat of vaporization. I'll hover this over the screen for a minute. Please take a look. Okay, so this has been our time. I'll conclude our session here because I've covered all the requisite topics for this particular crash course. For the subsequent session, which is happening very soon, I will be going over the entire concept of waves and light. Please do a thorough right reading of the concept. If you can join the session, please join us live. I'd be more than happy to take you through the concepts individually and help you understand and overcome your doubts for the same. Thank you.